Okay. In-flight structural sensing of helicopter landing gear using fiber bragg grating. The presentation that I'm going to show you is something different than the presentation you have seen at this moment, because it's nothing about modeling, it's nothing about testing, but is, let's say, an on-field test of the various methods that we have seen in the last few days. First of all, I would like to thank the partners. The CIRA, the Italian Aerospace Research Center, is a public company specialized in the most advanced aerospace research technique. The CIRA involved our group in the project that is called Angela. The Angela project is funded by the European Commission through the Clean Sky 2 joint undertaking. The project is aimed at design, manufacture, qualify, and test in flight an innovative landing gear that will be integrated in the RACER compound technology demonstrator of Airbus. Our task in the project was to equip the landing gear with an array of sensors to enable monitoring some physics quantity, some characteristic of the airplane, of the aircraft, in this case of an helicopter. It means the weight on wheel, the aircraft balance check that usual an aircraft have to perform first at the beginning of each flight. But most important, our focus is on the detecting the hard landing. What is the hard landing? What hard landing means? An hard landing occurs when an aircraft touches down the soil with a vertical speed or a force that exceeds the limits defined by the manufacturer. This often results in a rough impact with the runway that can potentially cause damage to the aircraft, and not only to the landing gear, but to the whole structure. The problem is that to date, there is no integrated avionic component that is capable of objectively monitoring whether a hard landing occurs or not. Usually, a company relies on the report delivered by the pilot, but at the same time, the 90% of the hard landing occurs by the wrong behavior of the pilot itself, so can't be objective as relay. This is the proposed method. The idea is to record the strain read by an installed set of sensors to identify the fundamental frequency by the FFT, the fast Fourier transformation, use the combination of the onboard data provided by the avionic of the airplane or the helicopter, combine it with the results of the FFT analysis to identify the impact speed. Identify then the range of the touchdown speeds that do not compromise the structural integrity on the aircraft, and then check whether the hard landing has occurred or not. The second partner are the Corpo Nazionale dei Vigili del Fuoco. It means the national fire departments. The test was performed in Ciampino Airport with the team of Daniele Tittoni. Let me say that they participate to the project, letting us the chance to use the Sikorsky S-64. This helicopter is called S-64 because it's entered in operation in 1964. So it's a 50s design. It's a very old helicopter. The avionic, the onboard equipment were renewed in the last few years, so the electronics is a new electronic, but the structure is a very old structure, an old concept. The idea was chosen just because, as you can see, it is a very distinctive structure, and it highlights the main landing gear that is the component that we are going to let me say, to test. Okay. What is our goal? Our goal, actually, our objective, is to verify that what have been already proven in lab work also on a real aircraft, on a real helicopter, because we have performed in the last few years several tests on, let me say, a bench test in laboratory. The scope is to stress the full chain. The chain is starting from the sensor, cabling, the interrogator, the data acquisition system, the processing, and the interpretation of the data under real operation condition, okay? What is our success? Our success is a successful flight, or better, show that we can use our system during a real flight, capture usable signals, being capable of using the the signals, and to show plots that convince our partner the system is viable and worth continuing. What does it mean, convince our partner? The Vigili del Fuoco are lending us a system, an helicopter, that has an average cost of more or less 20,000 euro for hour of operation. So at each hour, they spent 20,000 euro. This is the reason why it's very hard to convince them. So this is a feasibility and transfer test, not a performance limit test. We are not looking at a number, okay? There's an overall approach. There's an overall, let me say, structure idea that is a biomimetic idea. Biomimetic is the tentative to emulate the biological behavior. In this case, the concept of biomimetics applied in an attempt to emulate the peripheral nervous system of multicellular living things. It means our plane, our aircraft, our helicopter must be thought as the human body, okay? In this case, the nerve endings must be the sensor, the spinal cord, the communication bus, and then the brain, the processing unit. It seems to us that the best combination, the best sensor that fit this purpose are the fiber bragg rating. The functioning principle of the FBG relies on bragg reflection, where a periodic modulation of the refractive index within the fiber score selectively reflect a specific wavelength, the so-called bragg wavelength, from an incident broadband light source. Okay, it means that from, this is the lower bottom, okay. It means that entering from this side, the broadband meet the grating and reflect a specific wavelength. The specific wavelength is defined by the bragg condition, that is this one. The reflected wavelength shift in response to physical perturbation that can be strain, that can be temperature, enabling an interrogator to measure the wavelength change and consequently to the physical quantity. It means that our sensors are very sensitive to mechanical variation, to mechanical loading, and to thermal loading. Why the FBG? It is shown in the picture. Clear, it's not to scale, but it's in proportional representation. It means that we have a standard single mode fiber. The core is about 9 microns, is fused silica. The cladding is 125 microns. And the standard jacket, in this case, a polyimide jacket, is about 150 microns. It means that the sensor and harness dimension are extremely small. This allows to install the sensor, in our case, on the external side of the fuselage of the aircraft, but using the existing cables and cables trace and duct. At the same time, we can use this sensor for an embedded system inside, for instance, carbon fiber laminates. The second point is that the sensor is in fused silica, so it's a passive device. It is immune to electromagnetic interference. It means that it does not interfere with and it does suffer interference from other avionics systems. The third point is the multiplexability. It means that we can put many sensors on the same sensor chain. The measurement chain can be tailored. Each measurement point can be potentially measured different physical quantities, such as temperature, strain, and acceleration. On the same fiber segment of few meters, I can put several sensors occupying just one channel of the data acquisition system, and each point can measure a different quantity. So the idea is to develop an intelligent structure capable of detecting its own status and also what is happening in the environment, okay, in the operational environment. We performed in the last few years several laboratory testing using a drop tower. One of the interesting points studying the landing, the hard landing, is that scientists are trying to define, let me say, the limit velocity that a structure can reach at the impact. One of these values that you can find in the literature is about 2 meters per second, but it depends on several factors, it depends on the structure, and it's only a vertical velocity, vertical speed. For this reason, we performed this kind of test. We had some interesting results sharing the publication. And this is the test that I'm going to show you today. It's just the first test, a tentative test, okay? We use 4 sensors, 4 different wavelengths. The sensors were bonded on the 2 legs, let me say. S1, the first sensor, sorry for that. The first sensor on the right shoulder, the second sensor on the left one, and then S3, S4, the third and the fourth sensor. We use the data acquisition system of Technobiz aerogator that is qualified for flight, and the rate of acquisition is about 1 kilohertz. The aerogator is capable of reaching 20 kilohertz, if I don't mistaken. Few picture of the application, okay, of the test. The acquisition system was installed on the rear seat inside the cockpit. I wasn't actually allowed to fly with them, unfortunately, so I was just present in the moment of the installation of the sensor. The fiber passes through the existing pass-through alongside the fuselage of the sensor, and just a picture to show how the FBG were installed. Several conditions that showed that it was not a proper installation. It was not, let me say, a textbook installation. Usually when you install a strain gauge, a sensor that must measure the strain of a structure, you have to bond the sensor in very intimacy with the structure. Okay. In this case, for who know how work the aerospace paint, understand that here we have something like 8 different layers of painting. So it's not the best condition for our sensor, but we weren't allowed to remove the paint. Okay. This is one of the tests. Here you can see that the helicopter, we performed several tests. So just to show you some of them, on the first part, we have the taxiing phase. So he's running along the runway, and then the takeoff, you can see that the sensors are changing. Something is happening. Now we will try to interpret what is happening. This is more interesting, I think, that because the helicopter is flying, so it's not touching the soil. There's no contact with the soil. Sudden changes in altitude without touching the ground. Okay, unimportant stuff. We can see that there's a slightly a positive slope. This is because the sensors were not thermally compensated. What does it mean? That the sensors in this moment are measuring at the same time the mechanical load and also the thermal load. Okay. This is one of the problem that we encounter. Our raw data were completely corrupted. No information can exit from this data. We had to develop a specific MATLAB code to clean up the problem, clean up the corrupted data in order to reach this condition, and then combining them and normalizing the signal, we reach a good point. Let me see. What we have here. The first part show the flying helicopter. Then we had a sudden touchdown. We touched the soil very rapidly. And then take off again, flight, a harder touchdown, and then the runaway along the, the run out along the runaway. When you talk about runaway, you think the plane, okay, way of an airport. It wasn't like that. More close to the road of Rome in this moment, so full of, let me say, problem. Okay, so this was a problem to us to, let me say, process it for the interpretation of the data. Okay, what we performed, following our method, starting from the time domain. Here in the horizontal axis, we have time. Using the FFT analysis using an hand-windowing method, all the frame in several windows in order to identify the proper, let me say, fundamental frequency of each step. So we have the helicopter in flight, etc., etc. Let's go a bit further. Okay. here is shown family of frequencies, okay, that we, let me say, found in our analysis. I don't want to waste our time. Here is a resume. A repeating spectral family is presented across window 1 to window 8 with lines that are approximately 19 hertz and integer multiple about half kilohertz. Using, considering the, let me say, the fundamental frequency and considering the speed, we can, the actual speed, we can define what is the impact speed. In this case, was very, very difficult because we have several problems. We found intermittent frequency at 9.2 hertz, about window 5 and in window 5, window 6 for the non-linear order content. We had persistent band near 150 hertz, between 375 and 385. More important, the last one, 491, 494 hertz. Behave like structural local resonance of the gear assembly, but we weren't able to understand exactly which was the source of this vibration, okay? The FFT outcomes, anyway, that we observed on the helicopter match the laboratory pattern closely enough to validate the technology transfer and justify continuing the program. Final remark, the work represent only a preliminary field test that allowed us to test a continuous and real-time monitoring system on the landing gear of a real helicopter. It means a system that must live all along the operational life of the helicopter itself, which had already been tested in the laboratory on a scale model. The results were encouraging, despite the test being carried out under critical condition. Did we achieve our goal? Let me say yes. The flight executed with sensor operation throughout K phases, usable data captured and processed, expected feature observed, and let me say partner-facing plots produced that support continuation of the activity. This means that our second partner accepts to continue the project with us. So thank you for your time.